is we're going to use the warm-up to introduce function notation, which you've probably seen before, but it's been a while since we've done anything with it. And it's really just listening to what the equation is telling us, right? We want to do direct substitution when x is equal to 2. The one thing that you may not have done is this part right here. H of 2. So when you see that notation, that just tells you x is 2, so you're just going to plug in 2 anywhere you see in x. I actually want to make that a different color. So what I'll do then is take the original expression, and anywhere there's x, plus we'll plug it 2, and then you just have to use correct order of operations to simplify. So you can do this in pieces, you can do it kind of in your head. 2 to the third power, we always do exponents first, so 2 to the third power is 8. And then if I times that by 2 again, this portion will be 16. Well, 2 squared is 4, 4 times 4 is 16. 5 minus, or negative 5 times 2 is 10, negative 10 I should say. And then the plus 1, and then you can kind of do as much or as little as you want in your head. 16 and 16 is 32. 32 minus 10 is 22. 22 plus 1 is 23. So that's function notation saying that when x is 2, the output is 23. Now the reason why that's kind of important is another way to write that is the ordered pair x comma y. So I just wanted to throw that out there. We're not going to do a lot of that, but it's just kind of a review that it's good to have that in the back of our mind. When we deal with functions, h of x could also be called y equals, right? And that's something that as we progress through this year, we're going to go back and forth between y equals or h of x equals, or maybe it's g of x. It just is a function, and that's function notation. Okay, so we kind of got a lot for this first page of notes. Our goal today is to analyze polynomial graphs. And as we've kind of seen, graphs, well actually we really haven't seen the graphs of these polynomial functions, but they're quite interesting. They don't have one distinct behavior that always happens. So we have to kind of take the pieces that we know, and some of this is we're going to build off what we've learned already. So the title of today's notes, and by the way, if you're titling it, this is kind of a combination of section 5.8 in our textbook with hints of 5.2 thrown in there, if you go back at all and look through your textbook. So the first thing is we're going to talk about y-intercepts. And I think I can make this bigger. Let me see, I can't make it too huge, so hopefully I think we can kind of get that. So y-intercepts, and this is true for any function. I don't care if it's a polynomial, if it's cubic, quartic, but anytime you want to find the y-intercept, that's whenever x is equal to 0. So if you have an equation, plug in 0, and whatever number's left over will always be your y-intercept. And then x-intercepts, this is when the y value is 0, so you set the equation equal to 0, and then we solve. And we've done that. That's part of what factoring was, right? We broke it down into a bunch of factors. We took the polynomial, broke it down into its factors, and if we said solve, you just set it equal to 0. So hopefully those two pieces aren't new. The way we approach them might be new, but the understanding of how to find them shouldn't be. There's kind of a new term here called relative extrema. Think of that word as extreme, right? What are the extreme values? Well, those are maximums and minimums. So if you ever see the term identify relative extremes or extrema, the extrema is plural for more than one extreme. And we're talking about maxes and mins. So if I drew a very quick sketch here, maybe we have a polynomial function that looks like this. Well, how many extremas are present? We have one maximum, and then here we have one minimum. Now we do have to be careful. These are technically called local maxes and local mins. The reason why is the arrow goes on forever. So this maximum isn't the maximum out of the entire function. It's the maximum of all the points that are close to it. So you might see the word local thrown out there, and that just means of all the points right around it, that point is the highest. And this could be called a local minimum, because all the points that are pretty close to it, that is the lowest one. So we could see more than one max and more than one min, and that's what we will see. Or sometimes there isn't a minimum and just a maximum, and there's a lot of different combinations there. But I think we've talked about maxes and mins. We just haven't seen multiple ones. The term increasing and decreasing, you've discussed from Algebra 1. And it was really based off of the slopes. So here's kind of what I want you to think of. Is because our polynomials have different pieces, they kind of curve in different directions, if a function is increasing, then all pieces of that function will have a positive slope. And sometimes students just think of, well, increasing, isn't that the function that's going up? Yeah. So I'll show you on this quick little sketch that I drew. The function is increasing, and we always read it from left to right, like we're reading a paragraph, right, or a sentence. We go from left to right, so here my function is increasing until I hit the maximum, and then to get from the max to the min, I have to decrease, but past the minimum, I'm increasing. So that portion is increasing, and we will go over examples like this, so you don't have to highlight and do all that. I just wanted to show you. When is a function decreasing? Whenever the slopes are negative. So think of the point between a max and a min. The only way I can get down to a minimum from a maximum is if I go with a negative slope, or if my function is decreasing. Okay, so you're going to be asked to analyze these different parts of the graph and say which part is the increasing part. Sometimes there's more than one, or which part is decreasing, and sometimes there's only one. Okay? Sometimes it isn't decreasing, and it might be increasing the whole way. So we'll see different types of examples. When is the function positive versus negative? Okay, so I'll let you write that down. We'll talk about positive versus negative. So when I think of positive, I think of functions that lie above the x-axis, right? And when we're talking about positive we're talking about positive outputs. So if I look at this graph, anything that's above the x-axis here, so this portion right here, and this portion right here, those lie above the x-axis. So those would be considered positive outputs, so the function would be positive during that time. The function is negative when the values lie below the x-axis. So here, think of why these are true. Well, look at your y values. The y values are below 0, so therefore any number below 0 would result in negative. So that's another way to analyze graphs, is just looking at their outputs, positive versus negative. All right, this one it might take some getting used to. And I'll kind of show you something to build a little bit more on what's the difference between an odd function and an even function. And a very quick way to tell, just by looking at the graph, is if the arrows on the graph are pointed in different directions. So the example I drew, one arrow is pointing down and one is up. That's an odd function. Another reason why is the degree is odd, and I'll share that with you in a little bit. If it's an even function, then both arrows are pointed in the same direction. They're either both going up or both going down. Let's show you a quick little example just with the odd versus even functions. You don't have to draw this unless you want to. What if I told you to graph y equals x plus 3? Okay. We know that that's a linear model that has a y-intercept of 3. So, quick, really rough sketch. It looks like that. Now, is that an odd or an even function? Odd, for a couple reasons. The arrows go in different directions, so that's odd. But why is it odd? Because the degree is 1. Okay? So now, let's look at, maybe I shouldn't have wrote that yet, because I was going to ask you, but what if I gave you the equation y equals x squared minus 2? Well, we just studied quadratics. We know that it's going to have a y-intercept at -2, and its function is going to go something like this. Can you see why that's even? For 2 reasons. The arrows are pointed in the same direction, and that degree is 2. So, graphs you might not be super familiar with, but we will be eventually, is what if it was x to the 3rd? A cubic graph goes like this. It starts low and ends high, and you can see that that is the odd function, because one arrow is low, one arrow is high. And then if we just kind of kept going on with this pattern, again, I don't expect you guys to be here yet. We'll get here by the end of the year. X to the 4th is very similar to a parabola, except for just kind of, it's a little flatter. This is a super exaggerated x to the 4th. It's not as sharp of a U. It kind of flattens out more when you get closer to x equals 0. But you can see kind of that pattern. This is also an even degree. And then remember what a negative would do, since we're doing this. If I said graph y equals negative x to the 4th, all that negative would do would be flatten. This is not a great graph, but it would flatten that out, and it would reflect it over the x-axis. So it's opening downwards, but even though it's opening downwards, it's still an even degree. So that's just, you can tell very quickly by looking at the graph if it's odd or if it's even. Okay. All right, and then the next one we're going to do in the next slide is called end behavior. And this is probably brand new. So I'll let you guys just start with this side here. What is end behavior? Well, before we define it, it's talking about those arrows that we just explained. What direction are the arrows headed as you go to the left or the right? And it's a notation that we just got to get used to. The general definition for end behavior is the end behavior of a polynomial function is the behavior of the graph of f of x, or I think delta math here uses y. So remember, y and f of x are the same thing. And it's as x approaches positive or negative infinity. So we're going to officially use a new notation to describe this end behavior concept. Okay, so we're given a graph, and again, the details of the graph aren't important. When we talk about end behavior, we're looking for what is the end behavior of the graph. So what are those arrows doing as we go to the right or left? So let's take a look. If I can scoot this up so I can see both arrows. It's really the notation. So maybe before we even deal with the notation, let's talk about this. As x goes further and further and further to the left. So as x goes further to the left, which means we're headed in the negative x direction, where is my graph headed? What would you say? Say down, right? Now mathematically, down is not a super accurate word. So where are we headed? What numbers are we going to get close to if this graph keeps going further and further down? Negative infinity, right? We're going all the way down to the farthest number we could ever go down to, which isn't really a number, but it's a concept. So that means that my y values here are going towards negative infinity. Okay? Don't worry about that. That's just supposed to be an arrow. It makes it worse in here. But that's part of the smart board. Sometimes it works well. Now, notice that was when we went to the left. So as x was going to the left, the output is going down to negative infinity. Well, what happens as I go to the far right? Where are the outputs of this function headed? Positive infinity, right? A lot of times you want to say up, right? Which is physically accurate. You are going up, but mathematically, where are we going? We're going towards positive infinity. So that's what the graph tells me, but how do I write that so a person reading it can understand it? So here's how we're going to do it. The end behavior of the graph says, as x approaches negative infinity, that arrow, we're using the word approaches here. So if you see the word approach, that's what that arrow means. So if I read this like a sentence, as x approaches negative infinity, which means as I go to the far left of this graph, then the y values are approaching negative infinity, right? Because that's where it's going down. And again, we don't use the word down as a mathematical description, but physically that's how we identify it. It's kind of messy too. So again, down is not the accurate description. You have to use the notation. So now, what happens as x goes to positive infinity? So as x approaches, the arrow stands for the word approach, positive infinity, which means as I move to the far, far right of my graph, then the y value in this specific case is going up to positive infinity. And this might help. I actually have never written this before, and I thought maybe it would be nice. Because a lot of times it's just the notation. What does the x approaches negative infinity mean? It means as I go to the left of my graph. And then what's the green one mean? As x goes to positive infinity, well, positive x values are all the way to the right. So that's the end behavior. You do not have to write the words left, right, down, or up. I don't want you to write those. That's just our thinking. All right, and since I just threw this idea of what a turning point is, let's just look at this graph here and see how many turning points does this graph have. Since the turning point is just a max or a min, we're going to literally just count them. And that's it. So how many turning points does that graph have? Well, we can count. Here's a maximum. Here's a local maximum. Here's a local minimum. Here's another local max and another local min, which tells me I have 4 turning points. There's a connection here. There's a reason why that's important. I'll share with you, but we're not going to explore it a ton. I might throw an extra question in here. What do you know about the degree of this graph? It's an odd function, right? So the degree is odd because one arrow goes down and one arrow goes up. They're in different directions. Now, the connection to that is it's an odd number that has to be greater than 4. The reason why is if I change directions multiple times, that means there was a change in a power. So this degree, this odd degree, might be x to the 5th. It couldn't be x to the 3rd, though, because if I had an x to the 3rd, I wouldn't be able to turn from a max to a min 4 times. Okay? And again, we're not going to get into that greatly. I'm just going to take advantage when this comes up and talk about it. Now, it could be greater than 5, but we know it's at least 5 or higher. Okay, so let's look at this example, and I'd like you guys to get as far as you can on it, and I'll just share with you how we want to answer these questions. So, analyze the graph by answering the following. Well, if I say find the y-intercept, maybe I'll just do this one for you, and then I'll give you time to write it down. But what is the y-intercept right here when you're looking at the graph? Perfect. It's f. Let me just quick log this attendance in. It's f. Why do we know that? Well, the y-intercept is whenever x is equal to 0. So if I don't move left or right, where is the y-intercept? It's right there at f. Right, so because we don't have numbers here, we're just going to use the letters to describe. And what I'd like you to do is see how much of this you can answer, knowing that there's probably some you might not be sure how we want you to answer it. So I just want you to try it on your own, and then we'll go over it in a couple minutes. So what's true about the x-intercepts? Well, the x-intercepts are wherever the y value is 0, which is the x-axis. So I've got x-intercepts at the 3 following points. So we would say x equals a, x equals c, and x equals e. And those are all my x-intercepts. Identify the relative extrema graphically. What that means is identify your maxes and mins. So when I look at this, where do I have maximums occur? Well, we have to be really careful with A. Notice how coming up to A here on the left, all these points are lower than the points on the right. So this spot right here at A is called a flat spot, which is not a max or a min. It's just, there's a change. When we get into calculus, that's an important point, but right now it's just a flat spot. But B is what we would call a local, actually B is what we'll call the absolute max. We're not going to use that terminology really, but it is the absolute highest point on this graph. So that would be called the absolute max. And this is at the spot D. And then D is just a local min, because it's the lower point of all the ones around it. So I would just say a min is at D. And then point E is a local max. And if you're writing it, I guess it doesn't hurt to just throw out the words local and absolute. And then I like to use a highlighter to help identify the spots where it's increasing versus decreasing. So increasing, think of having a positive slope. As we go from left to right, is the graph going up? So if I start on the left-hand side to go up here, notice I have increasing slopes. And then it still is increasing. Even though it flattens out here, it's going to increase all the way until I hit B. So how do we write that? I didn't really tell you that directly. You could use interval notation, which means I'm increasing from negative infinity for x all the way until I get to b. Now, is that the only spot that we're increasing? No, because then I go from d to e is also increasing. So I might throw that interval saying, you know what, we're also increasing from d to e. And then wherever we're not increasing, we're decreasing. So decreasing from point B to D, that's going from a maximum to a minimum. And then here we're increasing from E all the way for the rest of the graph. So decreasing from B to D, and then E to, we would say, positive infinity. Alright, so when is my graph positive versus negative? Well, anytime your graph is above the x-axis, it's going to be positive. So we have to write the interval of where it's positive. Well, anytime we're at the spot from between A and C, we're above the x-axis. So we are positive from A to C. And then we aren't positive anywhere else. And then where will we be negative? We are negative anytime our y value is negative. So anytime we're below the x-axis. And then we just have to be careful how we write this, because this first chunk starts when x is negative infinity and it comes up until a. And then we have the chunk from C to E. All of that is below. And now here's where some people, well, technically, notice how E is 0. So is A and C. So we can't really say we're below 0 from C to infinity, because E we're actually at 0, and 0 isn't positive or negative. So then we have to finish by saying we're from E to positive infinity. So for the rest of the x values, from E to positive infinity, those will give me negative outputs. All right. Is this an odd or an even function? Even, right? How do we know? Both arrows go down. So because both arrows are going the same direction, it's an even function. my end behavior as x goes to the left. So as x goes to negative infinity, where's my graph headed? We want to say down, right? But we're not going to write down, we're going to write negative infinity. And actually, aren't both of the arrows going down? If they're both going down, that means the other one, as x goes to the far, far right, the graph is also going down, so they're both going to be approaching negative infinity. And then this one I just threw out there. How many turning points did we have? 3, right? Because look at my answer to the relative extrema. I had 2 maximums and 1 minimum. So your turning points are just the amount of total maxes and mins you have. And like I said, turning points is not going to be on tonight's homework, so I'm not super worried about that. Okay, so the next handful of slides, I don't want you to write. It's just getting used to how Delta Math is going to ask you a couple questions. And then we have one more topic that we have to discuss, and we will have you write that down. So don't write this, but what if I tell you to analyze this function right here? So I give you a graph, and we got to fill in the blanks. And so the degree of f is, and then if you hit the toggle, it's odd or even. So looking at this, odd or even? Even, right? Perfect. Even, because both arrows are going down. And the leading coefficient, now we didn't talk about that, but that's the a value. And what I want you to do is think of quadratics. What do you know about the a value if both of your arrows are going down? What caused it to go down? Is it a positive or a negative? A negative, right? And that's the same thing that we learned with quadratics, is if it was a U-shaped graph and the a was negative, it flipped it down. It's called a reflection over the x-axis. So there are blank, distinct, real zeros. Remember the word zero stands for x-intercepts. So how many intercepts are totally there? 2. Now there's something special about the way this graph goes and hits this spot and comes back down, and then hits and come back down. We'll talk about that here in a second. And then how many relative extremas are there? 3, right? Because what are they? There's maxes and minimums. And that's all that first part is going to have you do, right? So just taking our knowledge, analyzing the function. The cool thing is we did all of this without an equation and just by looking at the graph. Okay. All right, now here's the part, and this didn't appear as great as I wanted it to, but don't write these because I think it's better for you to look at the patterns. The question up here says, which equation choice could represent the graph below? Notice one thing, though, that the function is written in factored form. So one hint right away is this graph odd or even? Odd, right? So we know that this is an odd graph. So if I was to multiply all this out, I know that it would be x to the power of something. And that power of something has to be an odd number. Well, let's look at that really quick. What if I FOILed all this out? I have an x to the first, an x to the first, and an x to the first. So if all those were multiplied together, this would give me at least an x to the third, right? So I know that it could be that one. And same thing here, this is a 1, 1, 1, so this could be an x to the third. All of these actually could be x to the third. So that at least tells me every one is possible. But now the question is, where are the zeros? And this is where you don't have to do a lot of work. But if you look at your graph, let's look at the zeros. And it's saying negative 8. Actually, x equals negative 8 is an answer. X equals negative 6 is an answer. And x equals 0 is an answer. Well, if these are answers, What if I add 8 over to the other side? Right? Isn't that how we got negative 8? So x plus 8 has to be one of my answers. So I know it's not this option, because that's x minus 8. Same thing here. And then this one, if I add the 6 back over, I get x plus 6 equals 0. So that means I can't do this one, and by default, I automatically know it's that answer, but notice where this comes in. If I add 0 over, I still get x equals 0, but now I have all of those factors written out. So x times x plus 6 times x plus 8 is the answer to this function. So notice how we analyzed the intercepts, and that just gave me those answers. So it gets a little trickier when you have a problem like this. There's something interesting that happens with our graph. And I'll point this out. So here I have an even degree, right? It has to be even, which means this is 1, 1, 1. This would be an x to the third if I multiplied it all out. So I know right away that that is not an option because it has an odd degree. But if I have the expression x minus 1 as an answer or an intercept, and I move this over, that tells me I get x plus 1, which means it's definitely not this one or this one. So by default, I get 2 answers. But what's special about that? I get x plus 1 times x plus 1. Well, isn't x equals negative 1 the same answer there? And just a quick refresher, another way to write this would be x plus 1 squared, because it's the same thing times itself. So there's a special part on the graph called multiplicity, which means if I have an answer and I do not cross over the x-axis, then this answer is duplicated at least. It could be x to the fourth, but if you go from decreasing and then you hit the 0 and jump to increasing without crossing over, then this is a duplicate answer, so you can put a square there. Right? And that's the pattern I just want you to be aware of. Because look at this one. Make it a little bigger. Now right away, we know it's an odd degree. So if I want to, all of these, now notice how this is a square here. So this would be a degree 2, and this is a 1. So this would be x to the third if I FOILed everything out. And same thing with all of these. They're all going to be some form of x to the third. So we couldn't reduce anything out just by knowing it's an odd function. But let's look at the zeros. This is x equals 2. So if I move the 2 over, I get one of my factors has to be x minus 2, but notice it doesn't cross over to the x. It doesn't cross over into the positive side. So this is at least a squared there. But then here, I do cross from negative to positive. So this will just be a single answer, at least. And we get x equals 8. So if I move the 8 over, x minus 8 is a factor. So if I was to write out this function, I would have an x minus 2 squared and an x minus 8. And hopefully you can see which one that would be. Minus. So those patterns, and again, when it comes up and down right here at 2, that means there's a duplicate answer. Okay. So I'd like you guys to think about, if this is my graph, which option would it be? let's look at this. Both arrows are in the same direction, so it has to be an even degree. This is a 2 and that's a 1, so this would add up to be x to the third, so it can't be that one. And same thing here. Here's a 1 and here's a 2. That degree, total degree, would be 3. So I narrowed it down to 2 just by knowing if it's odd or even. And then I've got x equals negative 6, but if I move that over, that answer came from a factor of x plus 6. And here we get x equals 1. And if I move that 1 over, then I've got a factor of x minus 1. However, both of them touch the x-axis but don't cross it. So I have 2 duplicate answers there, which leaves me with x plus 6 squared times x minus 1 squared. So that's the idea of multiplicity, where it's just multiple answers shown in the graph. We're going to skip. No, we're not. This is the one I want you to write down. This will be our last one for today. You do not need a super accurate graph here. I'll just tell you which points you need to highlight as you're drawing it. So give me 1 second. And that goes by 2, so we got to go over 0. Okay. Those are the 3 points you need to know on your graph. So as you're drawing that, and then we'll do this in pieces so you don't have to write all the steps out at once. So the directions tell us to write a function in any form that would match the graph shown below. Well, as we just saw, all of the examples we saw were written out in what we call factored form. So we know right away 2 of the factors of this. Now we actually know more because of the multiplicity. So once you have a quick sketch, the first thing you need to do is just identify where's that y-intercept. And the y-intercept is whenever x is equal to 0, what's the y? That's pretty quick. So that point will come into play later on. The next thing we need to do is identify our x-intercepts, which we saw were x equals negative 1 and x equals 3. So those are just points in the graph. And then, as we did before, let's add the 1 over, and let's subtract the 3 over, so we write those as factors. But that's really what we're looking for. How do I write the factors given the intercepts? And then step 3 is write the equation in factored form. So you could put y equals here, or you could put f of x equals. And I'm going to leave a little space right here. You'll see why in a second. Because technically, these represent any functions. But we don't know if the a value, we don't know what the a value is other than it was reflected down. So you know your a value is going to be negative, but we'll find that a value. And there's one other thing we can do. Technically, this isn't correct right now. And the reason why is my intercepts don't cross over the x-axis. They hit the x-axis and then turn. And they hit the x-axis and turn, which is multiplicity. Because the graph turns, we need to put squares there to represent that x plus 1 squared has 2 answers for negative 1. And same thing here at 3. questions kind of how we got to this point right now? Kind of comfortable with where the x plus 1 came from, why it's squared. You might be wondering, why do we need the a? Right? The a is the one thing that, right now, this is not a true equation because a is unknown. And that's the next step, is how do we find that a value? To find the a value, we need to use the y-intercept. And y-intercept is the connection that's going to relate all of this together. Now, remember, what is the x-intercept? It's when x is 0 and y is negative 6. So what I'm going to do is take this expression up here, I'm going to put a negative 6 here, a 0 here, and a 0 here, and then notice the only thing that's going to be left over is the a value. So we'll be able to find that. So this will be what my work is. We're going to plug negative 6 in for f of x. And the reason why is if I plug 0 in here, f of 0 is negative 6. So when x is 0, the output is negative 6. That's why it is written that way. We don't know what a is. But I do know what x is. And notice the warm-up that we did today, just simplifying items similar to this. That's really our goal. So now we're going to use algebra to simplify. I'll get negative 6 equals 0 plus 1 is 1. Negative 3, 0 minus 3 is negative 3. And then you could square that. If you can do all that in your head, go ahead. You can save some steps. The only thing some students make a tiny error with is, remember when we square a negative, technically this is 1, this is negative 3 times negative 3 is a positive 9, so 1 times 9, or really a better way to write this would be 9a. And then I have to solve for a. So I just have to move the 9 over to the other side with division. And then 6 over 9, that reduces down to negative 2/3. Alright, so that was a lot of work. Finding the a value is the most amount of work. It's the hardest thing. And then our last step is, now that we know what a is, we're going to use a to write the exact expression. So I'm going to go back up to the very top of the screen. And I'm going to say, well, what was f? F of x is the a value times by the factors squared, x plus 1, and x minus 3 squared. And there is the exact equation that gave me that graph. And if you want, you could grab your calculator right now, plug that entire function into the y equals and graph it, and you should get the exact graph that we have up there. So what do we take away from this? Okay, I'll come back to this slide. I just want to quick show you. The y-intercept helps us find the a value. The factors help us set up the original function, but this function is not distinct until I find exactly what that a value is. So then the a value combined with the y-intercept, that's how I found negative 2/3, and I can write the exact expression. It's a lot. Right? It takes a while to get used to. Oh, sorry. I don't like what just happened there. All I wanted to do the school day. All right. Let me see which one. We don't want that one. Let me show you just another process. This is basically the same thing. I don't want you to write this one. I think it's just nice for you guys to see another example, follow the process, and you'll see it's a lot quicker once you get rolling. So, when I look at this, where's my y-intercept? This is at the spot over 0, down 30, 0. Okay. What are the x-intercepts? Well, this one crosses at x equals -5, and there isn't a multiplicity because it goes through the x-axis there. So I know that x equals -5 is one answer, and x equals 3 is the other. But to write this in factored form, I need the factors of those. So I just got to move the 5 over, and then, oops, I write that so that's neater. And then I move the 3 over with subtraction. So f of x is equal to x plus 5, x minus 3. So there's the a value there. And at x equals 3, we have the multiplicity, so that one has to be squared. So now, I'm going to use the a value. So -30 is going to go in the f of x or the y spot, and 0 is going to go here. So I'm just going to solve. So I know that I'll get 5 here, and I'll get -3 squared, which is 9. So I'll get 5 times 9, which is 45, times 8. And then I'll divide by 45. And you could divide those by 15. So we get 2/3. And it's pure coincidence that this -2/3 is the same as the last example. But then I'll write my answer. And there you go. So, we don't have this one. We're not going to do this one, but I just wanted you to know that you could describe all of this stuff without looking at a graph, just by looking at the degree and the leading coefficient. Right? You know if it's odd or even. You know if it's increasing or decreasing because of the a value. So, tonight's homework is on Delta Math. It's called Polynomial Graphing. We do have a quiz on Friday. So you want to make sure you're all caught up and be ready for that quiz on Friday on Schoology. All right? So that's all I got. Adios. Have a good day, everybody.